Thank you for coming. My name is Mahshid. I'm Michael Bowling's first-year master student, and I'm going to talk to you about the project I've been working on for now about 3 months, cloud coding for count-based exploration. So let's have an overview of the talk. We will discuss two popular exploration methods. One of them is count-based exploration, of course. We'll talk about why they don't really work on large environments, and we'll give a simple solution, cloud coding, spoilers, to have them work on large environments, and we'll show some results. So let's begin from the top, RL setting. In RL, we usually have an agent and environment. The agent takes the state and the reward from the environment and takes an action according to its policy. And then the environment will give the next state and the next reward. The goal of the agent is to maximize the cumulative reward. So it would make sense for the agent to pick the action where it would receive the best reward, or basically the best future rewards. But the agent doesn't know everything about the environment, so it wouldn't necessarily know which action is the best to produce rewards. So we'll have to take action which it's uncertain about. So here we come to the exploration-exploitation trade-off. The agent can pick the action that it knows will produce rewards. It's exploiting its knowledge of the environment, or it can pick an action which the agent is uncertain about. So the action that really haven't been selected, the agent is uncertain about this reward. So here we have an example. For example, you're going camping. You want to set up a tent. You find a nice spot, but maybe there's a nicer spot someplace else. So you will have to look. So it's a trade-off. It's really not solved yet in RL. My work will focus on the exploration part. I want to give a method for exploration, and that works maybe better. So if you want to explore, what is a logical thing to do? That's the basic thing to do. I'll select actions randomly. And that's basically a method. Epsilon gradient is a popular method. I will select actions randomly, exploration, with epsilon probability, and I will select actions with probability 1 minus epsilon, which is, I'll select the greedy action with probability 1 minus epsilon, which is the greedy action. It sounds simple enough, and a lot of the state-of-the-art agent architectures still use this method, like Dreamer, like Rainbow. And it selects actions without any discrimination. So we're basically rolling a dice. I will roll a dice to see if I want to explore or exploit that right now. And if it lands on exploration, I will roll another dice to pick the action that I want. And I think maybe we can do better than rolling a dice. So is epsilon really good? There's some environments epsilon really can fail, basically. One of them is the reversal environment. To introduce this environment, it's a 6-state environment. At any state, you can pick action left or right. If you pick the action left, you'll definitely go left. Of course, in the first state, you pick left, you'll stay where you are, and you will gain a reward of 5. But if you choose action right, there's only 30% chance that you would advance. There's a 60% chance that you would stay in the same state that you are. And if it happens in state 5, you would get a reward of 10,000, which is the main reward that we want. And there's a 10% left, so there's also a 10% chance that you would go backwards. And if we think a little about it, how epsilon greedy would perform in such environment. So imagine the agent has discovered the left side reward, which is the distractor reward. So the greedy action will always be left. So it would pick an action a random action with probability epsilon, and that random action would be right with probability half the epsilon. And so, and there's only 30% chance that you can advance with that. You do the math, it will take epsilon really a long time for it to explore and reach to the right side, which is the main reward. So there are other methods we can do. There's a count-based exploration method. It's simple. There's a state. We can pick some actions, and I'll assign an integer to each of those actions, which is the visitation count for each of the actions. So here, for example, I visited the up action 3 times. And I want to visit the action that has, I want to entice the agent to visit the action that has the lowest count, basically. So one thing I can do is to add an intrinsic reward that's inspired by the UCB formulation, upper confidence bound. And so here we change the reward from the external reward only to external reward plus an intrinsic reward. And as you can see, the intrinsic reward would go down as the number of visitations would go up. There's also a term log of state visitation counts in the denominator, which would want to keep the exploration going for a while. And so the lower the visitation count, the higher my intrinsic reward is, the higher the agent, the more agent would want to visit that action. And there's also a coefficient beta. It's a hyperparameter. It's a knob I'll tune to see how much exploration I want, basically how much exploration I want. So is this a better method or not? Yep.
Sorry, question.
Yeah.
What's your objective here? Is your objective to reach the 10,000 reward state as soon as possible?
Yeah, basically. To explore enough to get to the main reward.
Or do you just want to reach there, or you want to reach there as fast as possible? Like, what's your objective?
What's my objective? Well, as an exploration method, I would want to reach the main reward, not the distractor, as fast as possible.
So you want to construct a policy which reaches the high reward state as soon as possible. Like that's, so if you run your exploration algorithm, you want to put a policy that reaches this high reward state as soon as possible.
It depends on what beta you set it to, but I want to insert something that explores actions that haven't been visited yet. So yeah.
So it's not necessarily as soon as possible, but
Yeah.
just quicker.
Yeah.
Like something faster than epsilon. Like something faster than epsilon 3, right? So epsilon 3 is, takes exponentially.
You have discounted, right?
Yeah, I'll explain it in the experiment section. So is this a better method? UC methods are popular in bandit settings. For me, count-based exploration algorithms make more sense. They're more intuitive, at least. The epsilon tree, which selects an action randomly, and they have theoretical guarantees. So all said, count-based exploration algorithms should work great in tabular settings. So why do we think they won't work that great in non-tabular settings? So we have a big world. Imagine a scenario where you're in Canada, you want to fly somewhere in Europe, you have a plane ticket, and you're starting in Europe. You're in state 1, you move an inch, and now you're in state 2. And now that's a whole different count. Now your count is set to 0. You have to explore the state as a completely new state. And it will be a lot of states between Canada to Europe. So it will make the agent explore a lot, explore each state. But we live in a large environment. There are many states. States are rarely visited. So we need something to generalize counts over the states. I'm not the first person to notice this. There's been work before to do this. There's this unifying count-based exploration paper, pseudo-counts. There's this other one that does neural density models. There's this hashing one, models to successor representation paper, random network distillation. And so what do I think about these methods? For me, these methods are complicated. They're too complicated to use. And they're difficult to understand. And if you read some of these papers, they're difficult to implement as well. So if you look in the community, generally people don't use pseudo counts for exploration. And yep.
Why do you say that CPU is difficult?
Oh, it's not like, okay, maybe my title is bad. It's not UCB, it's these.
The UCB thing that you showed before.
No, not that.
That's okay, right?
Yeah, yeah.
Okay.
The ones that try to make counts work in non-tabular setting. And so, and again, on the other hand, we have epsilon greedy, which is extremely simple, and you can code it in 4 lines. And even if you want to discuss the gains you would get with those papers, there's a paper on bonus-based exploration that does exactly that. You can read that and see how much benefit you gain from using those methods. So what do I need? What do we need for an algorithm? I want my algorithm to work with functional approximation. That's the whole point here. I want it to be relatively simple, so people would use it as opposed to epsilon greedy. And it should work better than epsilon greedy, right? We have encountered this problem before, I feel. We had value function, and we were in a tabular environment. We went to non-tabular, and one of the first things that we did was tile coding. What's tile coding? Here we are. Imagine agent in a continuous environment. We want to discretize the environment, so we would put partitions here. So each of these partitions we'll call a tile, and the whole partitioning is called the tiling. And we'll offset these and put a bunch of them. So here we are. So the agent is in 3 of these tiles from 3 different tilings, and we'll use this tree to approximate the value function. We have the same problem with counts. We were in a tabular environment, we went to non-tabular setting. What can we use? Maybe tile coding can be an answer. So here we are. We're going to use tile coding for counts. So there are n tilings. They're a little bit offset from each other. Each tile would have its own individual count. So since an agent is in n different tiles, we would get n numbers. So here, the red tiling would give me 4, for example, and the green one would give me 5. But I only need 1 count. So I'm going to aggregate these numbers together. With value function, yeah.
What's the file over
The partitioning?
Yeah.
Yeah, it's over state. So with value function, what we did was average. I'm just saying maybe average isn't the best method. Maybe it is, maybe it's not. For counts, to represent counts. We can try with a bunch of different functions. Average, min or soft min, max or soft max. And so we get to the experiments that I'm running. Again, I'm running my experiments on RiverSwim, which I showed you before. Here it is, MVP. There are 6 states, and the actions you can pick are left or right. My experiment setting is it's continuing. I'm running these for 100,000 steps, and they're discounted. The baselines which I'm comparing to are epsilon greedy and the exact count method. And so these are my results. The x-axis is the time step, The y-axis is the undiscounted return. And the two plots, which I'm not sure if you can tell the difference in color. There's blue and green on the top. It's tile coding with min and exact count, which they're matching the performance. Tile coding with min is matching the performance of exact count. The two on the bottom, red and purple, are tile coding with average and max. And the black one is epsilon greedy. So, they're beating epsilon greedy, but tile coding with min matches the performance of exact count, which is understandable. Since we're in an environment that is tabular, it doesn't need generalization. So I wanted to go to an environment that I needed generalization. Basic step I could take, make the environment I was in, and make it continuous. So here we are, continuous reversion. Not a lot has changed, except the state is now the distance from the beginning of the river. And now we have an area on the left and the right, which will yield the reward. If on the left side I take the left action, I'll get the reward of 5. On the right side, if I take the right action, I'll get the reward of 10,000. And of course, the actions I can choose from is left or right. I have a step size with some noise. Setting is again continuing discounted and will run for 100,000 steps. The baseline is epsilon greedy, but now I cannot have exact counts now I can't have exact counts with continuous environment because I can't put count on every number between 0 and 1. So as a baseline, I proposed to have a state aggregation, which is basically one tiling. So we would compare if the added tilings would help the with exploration or not. So, and this is the result. The x-axis is again time step, y-axis is undiscounted return. And the two plots on the top are tile coding with max and average. The variance is huge, but it still performs a lot better than the other methods. So the two plots, it's red and green, they're almost like on top of each other, so you just see a red line. Are state aggregation count and tile coding count with min. And the purple one on the bottom is epsilon greedy. So they're definitely beating epsilon greedy. And the max and average seem to do a lot better than state aggregation. So this is where I am with my results.
It's an interesting shape. Why do you think that is? Because it stops getting reward in the middle there. And then it starts again.
I'm not entirely sure. Maybe I think it will take enough right actions that now left actions have the less counts, and it would take the left side more.
And then it gets stuck there for a while.
Yeah. So maybe it's that. This is where my project is. For the future, what I can do for the future is bring this method to another environment, a larger environment. A natural step would be to work in Dreamer v2. Dreamer version 2 already builds a discrete representation of the observations. So basically, discrete partitions, that's basically tile coding. And I can easily put counts on that. Or I can go to Majoko. Majoko has high dimension observation space. So even putting tile coding would be challenging on that because that would grow exponentially large, and that's something I should consider for that. And that brings us almost to the end of the talk. To have a summary of it, we talked that epsilon greedy is really popular, but it takes actions randomly. Counting exploration methods could be better. They're more intuitive at least. And but they can't be really used for functional approximation. There's been some previous work to remedy this, but a lot of them are complicated to implement. So maybe tile coding would be a simple solution to make count-based exploration in large environments. And I showed some results on river swim and continuous river swim, which is promising that tile coding can help. Thank you very much for your attention. I'm very open to questions.
I've got a question.
Yeah.
But I'm gonna make you jump around slides.
Okay, good.
So if we go to the last set of plots you had on the continuous river swim.
Yeah.
So the best there is the max, and
Yeah.
then the average, and then everything else is scalar.
Yeah.
And then if we go to the discrete river swim, the min and is it the min and the average, or is it just min and exact count are best?
Yeah,
and everything
exact
else is best? Do you have any intuition for why that's the case?
For the discrete river swim, I guess exact count is the best because we don't need generalization. And tile coding count with min is the closest to exact counts, I feel. So you would take the min of all tiles. With the continuous, I really don't have the intuition. Maybe it's because yeah, maybe the average is like using the counts for other tiles. Min is just taking the minimum. I'm not sure why they're a lot better.
So you modify the reward
Yeah.
by some number.
Yeah.
That may change the optimal policy. Is that correct?
Yeah.
And is there a way to deal with that? To let's say maybe in these specific problems does not change the policy? Like, is that what we care about here? Or
There is a way to deal with that. You can so instead of adding the intrinsic reward to the external reward and have a whole different reward function, you can decouple the Q. You learn one Q for the external reward and another for the counts. And so you would keep the Q with the external reward function, but I haven't tried that for my experiment. Yeah.
Are you saying that's like what UCD does? Like where it's the value, not when you select action, you add an extra value to each of your actions when you choose it. And you still learn the same, like the action value is learned independently of the exploration term. Is that what you're suggesting?
I think. Yeah, you decouple the exploration term from the action value term that you have, so you would keep the Q with the external reward like clean, basically. Yeah. Yeah.
the long term does it change the optimal policy?
I don't think so. Intrinsic reward. Yeah. I don't think in the long term it would change the policy because the intrinsic rewards are going towards 0. So the expectation would be 0.
So based on this intrinsic reward structure we have, so there is a particular value of n at which this value inside the square root starts decreasing instead of increasing.
Yeah.
Right. So how do we choose that? Because right now, I think that there is a constant value of n for this function. When this log n over n starts to increase and decrease instead of increasing. So how do we?
It will decrease in the it will start decreasing.
Yeah, but that will happen at particular value of n.
Yeah.
And that might be different. Like different environments might need different explorations, multiple explorations of the same state.
I don't know at which point. So what you're saying is that at some point the slope of the loop is greater than the denominator?
Yeah, it's less than the denominator, so this overall value will start decreasing. That's what we want with this intrinsic value.
Yeah.
That as the n increases, this reward increases.
Yeah.
So initially it has a positive reward and later it does not come. But how do we choose basically when to start increasing the reward? At which value of n does this happen for different environments? So how do we choose that value of n, or how does this model?
Like we start the count from 0.
Yeah.
Of course, like there's a 0 divided by 0 problem here, so we should start at something.
Let's say we start from 1.
Yeah.
Right. So let's talk about the discrete swimmer environment. So in that, the n will be from, let's say, 1, 2, 3, 4.
Yeah.
Right. So that will give us some shape of the curve for this. I'm
Yeah.
sure you apply that. And even for the continuous one, if like we go from n1 to 3, 4, it will give us the same value.
Yeah.
But the explorations in both of the environments might, the exploration requirement might be different. So how does this count that?
I'm not totally sure if I understand the question.
Can I answer?
Yeah.
Yes.
The rule of denominator is faster than the numerator. So at some point, it's gonna start to decrease, right?
Exactly.
So even enough visitation of the state and action SA, the denominator will be.
No, that's what my point is. What if I don't want it to decrease up to a certain point? Let's say I want it to. What if it takes just 10 steps and then it starts decreasing? But let's say we needed 100 explorations to some state to get the actual record.
So
you're
it should be. No, but he has a good point. It's a non-stationary environment.
Yeah.
And this goes to 0, and like
Yeah.
what Mike was saying, you get the same policy. So it's only going to complicate.
Yeah, it needs
Yeah.
to be stationary.
Yeah, unless you do something. Yeah. So like you want non-stationary, you have to do something about the counts.
Yeah, this I'm not considering stationary, so I'm not sure how we can change this for non-stationary problems. Yeah.
And if you just do like the last n counts, then he's, something.
That wouldn't necessarily go to 0.
Yeah. Then it,
So it's like 19. It's the one with the.
Yeah.
So the shaded region is some statistics about the like variance or confidence about the mean, correct?
It's confidence.
Understand. So it's possible because the shaded regions look very smooth and nice looking and white, and actually some of the seeds just failed and some are very good. And that mean is not representative of how the actual agents are behaving. So perhaps plotting the individual seeds will help you more
Yeah.
based on that shape.
Yeah, that's a good comment. I should look at the individual seats.
Have you seen any post difference or changes in the file size of giving there? At the beginning of
I haven't tuned them. I just changed them arbitrarily. So this is one tiling, like one configuration that generates this plot. Of course, if you change the tiles, number of tiling, it would be different.
do you think about maybe the problem? Maybe it's starting from big files and then gradually shrink them because of more accurate reads, that would be a good thing. But then the number of counts
Yeah.
will change.
The number of counts then don't represent it.
Yeah, but after the phase of learning, like concepts about the environment. You can, for example, add more grids on E, for example, that toy that have.
Yes, but the table for your counts would be expanded.
Yeah.
And you would run the same.
It buys some. If you gradually increase your resolution, the time.
Can you
have to be
keep the same
careful-
thing?
You have to be careful at how fast you shrink them. Like some of these, you shrink them really fast. Yeah, I think you might just then have more and more, like, and you're in this problem, there's so much to explore that I never explore it. But maybe it's some sort of right way. I don't know what to do with the existing counts and how to assign them to the smaller tiles. I also don't know whether you could just get the advantage of starting many different tiles that are all big. Like that's how coding likes to have big tiles. And it tries to get precision by having lots of tiles.
Actually, it depends, so, because like here max is best, so then you probably don't want, like, the size of how max, if you average, I don't think max is
It's-
how, if you do max, that's true.
I think trying to figure out, like, we've been talking a lot about that sort of how do you use this aggregation function. We have these many different partitions. And the fact that max is big, I don't think is the end. It's the end of this that story.
Yeah, there's a lot more there.
Other question?
You just click on the chat.
Chat on the top.
Yeah,
Thoughts on how to scale up tile coding when state dimension is high. Yeah. So, like one idea, I haven't explored this, but one idea is that we can put tile coding, but like pairwise dimensions. So you would take 2 dimensions and put tile coding on those instead of tiling the entire thing. Does that answer the question? Is there any other question? Yes.